The mysteries of space have captivated humanity for centuries, igniting the flames of curiosity that drive scientific exploration and philosophical inquiry alike. We gaze up at the night sky, overwhelmed by the sheer scale and complexity of the cosmos, grappling with questions that seem to stretch beyond the limits of our imagination. Where did the universe come from? How did it begin? And perhaps most mind-bending of all, what is the true shape and nature of the universe itself? These are questions that challenge not only our knowledge but our ability to perceive reality. But before we continue, subscribe so you don't miss out on any of these videos. At the forefront of this exploration lies the theory of cosmic inflation, a groundbreaking concept in cosmology that attempts to explain the very earliest moments of our universe. Before the universe as we know it began its slow and steady expansion, there was a brief, violent phase of rapid inflation. But what does this mean? And how does it shape our understanding of the cosmos? To comprehend this mysterious phase of inflation is to unlock clues about the very structure and destiny of the universe itself, including questions about its shape, its ultimate fate, and whether there are other universes beyond our own. Cosmic inflation is a theory that emerged in the late 20th century as a solution to several perplexing problems within the standard model of cosmology. According to the Big Bang theory, the universe began as a singularity, an incredibly hot and dense point that expanded outward over billions of years to form the vast cosmos we observe today. But this model, while successful in explaining much of what we observe, left certain puzzles unsolved. One of these puzzles is the so-called horizon problem. The horizon problem arises from the observation that different regions of the universe, separated by vast distances, appear to have nearly the same temperature. This is surprising because, according to the standard Big Bang model, these regions should never have been able to communicate with one another. In the early universe, information could only travel as fast as the speed of light, and there simply hasn't been enough time since the Big Bang for these distant regions to exchange information and reach the same temperature. Yet they have. Enter the theory of cosmic inflation. In the early 1980s, physicist Alan Guth proposed that, for a fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. During this phase, the universe expanded much faster than the speed of light, solving the horizon problem by allowing distant regions to have once been much closer together. Before inflation, these regions were in causal contact, meaning they could exchange information and reach thermal equilibrium. Then, during inflation, the universe stretched so rapidly that these regions were flung far apart, explaining why they now appear so similar despite being separated by billions of light years. But cosmic inflation doesn't just solve the horizon problem. It also addresses another mystery known as the flatness problem. The flatness problem refers to the fact that the geometry of the universe appears to be very close to flat, meaning that, on large scales, space is neither curved inward like a sphere, nor outward like a saddle. This is surprising because, according to the standard Big Bang model, the universe's geometry could have evolved into a curved state over time. Yet, observations of the cosmic microwave background radiation, the afterglow of the Big Bang, show that the universe is remarkably flat. Inflation offers an elegant solution to this conundrum. By expanding the universe so rapidly in its earliest moments, inflation essentially smoothed out any initial curvature, stretching space so that it appears flat, much like how inflating a balloon makes its surface appear flatter the more it expands. This rapid inflationary period created a universe that looks flat on large scales, even though it may have started with some initial curvature. But what is the mechanism behind inflation, and how does it work? The exact details of inflation are still a matter of theoretical investigation, but the basic idea is that inflation is driven by a hypothetical field called the inflaton field. This field, which permeated the early universe, had a peculiar property. It could store a vast amount of potential energy in a stable configuration. As the universe cooled and expanded, this energy was released, driving the rapid exponential expansion of space. Eventually, the inflaton field decayed, releasing its energy into the universe in the form of particles and radiation, kickstarting the Big Bang as we know it. One of the most intriguing implications of inflation is the idea that our universe may not be the only one. In many models of inflation, the process doesn't just happen once. Instead, it continues indefinitely in some regions of space, giving rise to what is known as eternal inflation. According to this idea, while inflation may have ended in our local patch of the universe, allowing the cosmos to settle into a more stable phase of expansion, inflation continues elsewhere, constantly generating new, bubble universes, in a vast multiverse. In this multiverse scenario, each bubble universe could have its own distinct properties, including different physical laws, constants, and even dimensions of space and time. This raises the tantalizing possibility that our universe is just one of many, an idea that stretches the limits of both science and philosophy. If the multiverse is real, then the question of why our universe has the particular properties it does may be explained by the fact that there are countless other universes with different properties, and we just happen to live in one that supports the formation of galaxies, stars, and life. While the multiverse hypothesis is speculative, it has gained serious attention from physicists because it offers a potential solution to some of the deepest mysteries in cosmology. For example, why does the universe have the precise conditions necessary for life to exist? This question, known as the fine-tuning problem, has long puzzled scientists and philosophers alike. If there are infinitely many universes in the multiverse, each with different physical conditions, then it may simply be a matter of probability that we find ourselves in a universe that happens to have the right conditions for life. In other words, the multiverse could provide a natural explanation for the apparent fine-tuning of the universe. Of course, the multiverse hypothesis raises profound questions about the nature of reality itself. If there are other universes out there, can we ever detect them? Is it possible to travel between universes? Or are we forever confined to our own cosmic bubble? These are questions that remain unanswered, and they may ultimately lie beyond the reach of empirical science. Yet, they provoke deep reflections about our place in the cosmos and the limits of human knowledge. Returning to the question of the shape of the universe, inflationary cosmology has profound implications for this as well. The shape of the universe is closely tied to its geometry, which, as we mentioned earlier, appears to be flat on large scales. But the exact shape of the universe is still an open question. One possibility is that the universe is truly flat, extending infinitely in all directions like an endless plane. In this scenario, the universe has no boundaries and no center, continuing forever without looping back on itself. Another possibility is that the universe is curved in such a way that it forms a closed, finite shape, similar to the surface of a sphere. In this case, if you traveled far enough in one direction, you would eventually return to your starting point, much like how circumnavigating the Earth brings you back to where you began. While this may sound strange, it is a perfectly valid solution in the context of general relativity, Einstein's theory of gravity that describes the curvature of space and time. Yet another possibility is that the universe is open and curved like a saddle, meaning that it would expand forever but never curve back on itself. Each of these possibilities, flat, closed, or open, has different implications for the ultimate fate of the universe. A flat or open universe would continue expanding forever, while a closed universe might eventually stop expanding and collapse in on itself in a big crunch, the reverse of the Big Bang. The question of the universe's shape is closely related to its overall density. In cosmology, the critical density is the density of matter and energy that determines whether the universe is open, closed, or flat. If the universe's actual density is exactly equal to the critical density, the universe is flat. If the density is greater than the critical density, the universe is closed and curved like a sphere. If the density is less than the critical density, the universe is open and curved like a saddle. Observations of the cosmic microwave background and the large-scale structure of the universe suggest that the universe is very close to flat, but whether it is perfectly flat or just very close to flat remains an open question. Even a slight curvature could have profound implications for the universe's fate and structure on the largest scales. The study of cosmic inflation and the shape of the universe is not just an abstract intellectual exercise. It has practical implications for our understanding of physics, cosmology, and the fundamental nature of reality. Inflationary models are deeply connected to quantum theory, the branch of physics that describes the behavior of particles on the smallest scales. In fact, the tiny quantum fluctuations that occurred during inflation are thought to be responsible for the formation of galaxies and other large-scale structures in the universe. These fluctuations were stretched to macroscopic scales by inflation, seeding the growth of the cosmic web that we see today. One of the key pieces of evidence for inflation comes from observations of the cosmic microwave background radiation, which is the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old, and it contains subtle patterns that reveal clues about the universe's early history. These patterns, known as temperature anisotropies, are believed to be the fingerprints of inflation, imprinted on the universe during its first moments of existence. By studying the cosmic microwave background in ever greater detail, scientists hope to learn more about the exact nature of inflation, including what drove it, how long it lasted, and whether it left any detectable imprints on the universe that could provide further insights into its origins and mechanics. One of the key goals of modern cosmology is to refine our understanding of the inflationary period, potentially uncovering new physics that could revolutionize our understanding of the universe. Cosmic inflation, despite its successes in solving the horizon and flatness problems, still leaves many unanswered questions. For example, what exactly triggered inflation to start, and why did it stop? While the inflaton field is a theoretical construct that explains how inflation might have occurred, its origins and nature remain speculative. Scientists have proposed various models of inflation, each with different predictions about how inflation began and how it might have ended, but there is still no consensus on which model, if any, is correct. Moreover, inflation raises the question of whether the universe we see is just a tiny fraction of a much larger, more complex reality. If inflation occurred as described, it may have stretched the observable universe to such an extent that we can only see a small patch of the total cosmos. Beyond the observable universe, there could be regions with entirely different physical conditions, possibly even other, bubble universes, created by ongoing inflation in other parts of the cosmos. This leads us back to the idea of the multiverse, a concept that has sparked heated debates among physicists and philosophers alike. The multiverse theory, while intriguing, also challenges our ability to test and observe such a vast and seemingly unreachable reality. Since we are confined to our observable universe, we may never be able to directly detect other universes, making the multiverse a topic that straddles the line between science and philosophy. Nonetheless, the multiverse remains a serious area of theoretical investigation, especially in light of inflationary models that naturally lead to the idea of multiple universes. Another fascinating aspect of cosmic inflation is how it relates to the concept of quantum fluctuations. In quantum mechanics, particles and fields are governed by inherent uncertainty, leading to random fluctuations in energy levels. During inflation, these tiny quantum fluctuations were magnified to astronomical scales, giving rise to the large-scale structure of the universe. This means that the galaxies, stars, and even planets we observe today are, in a sense, the result of random quantum fluctuations that occurred during the first moments of the universe's existence. This realization has profound implications for our understanding of the universe's origins. It suggests that the initial conditions of the universe were not predetermined or finely tuned, but rather the result of random quantum processes. In this view, the structure of the universe, from the distribution of galaxies to the formation of solar systems, is a direct consequence of quantum randomness amplified by inflation. This challenges the classical notion of a perfectly ordered and deterministic cosmos, instead painting a picture of a universe that emerged from randomness and chaos. Yet, despite this randomness, the universe exhibits a remarkable degree of order and coherence on large scales. This is one of the great mysteries of modern cosmology. How can a universe born from quantum uncertainty evolve into a structure as complex and organized as the one we observe today? The answer may lie in the delicate balance between order and chaos that defines the universe's evolution. Inflation not only provides a mechanism for smoothing out the universe's initial conditions but also for generating the seeds of cosmic structure. As inflation stretched space, it amplified quantum fluctuations into density variations that would later grow into galaxies and clusters of galaxies under the influence of gravity. These density variations, while tiny in the early universe, became the scaffolding for the cosmic web, the vast network of interconnected galaxies that spans the observable universe. The cosmic microwave background radiation, which is often described as the echo of the Big Bang, contains imprints of these early density fluctuations. By analyzing the patterns of temperature fluctuations in the cosmic microwave background, cosmologists can infer the distribution of matter in the early universe and trace its evolution over billions of years. This allows scientists to test different models of inflation and gain insights into the universe's initial conditions. One of the remarkable features of inflation is that it predicts a nearly scale invariant spectrum of fluctuations, meaning that the density variations generated during inflation should look roughly the same on all scales. This prediction has been confirmed by observations of the cosmic microwave background, providing strong support for the inflationary paradigm. However, there are still open questions about the precise nature of these fluctuations and whether they contain any signatures of exotic physics beyond the standard model. In recent years, there has been growing interest in the possibility that inflation could have left behind detectable primordial gravitational waves, ripples in the fabric of space-time generated by the rapid expansion of the universe during inflation. These gravitational waves would be incredibly faint, but if detected, they could provide a direct probe of the inflationary epoch and reveal new information about the earliest moments of the universe. Several experiments, such as the BICEP and Polar Bear collaborations, are currently searching for these primordial gravitational waves by studying the polarization patterns in the cosmic microwave background. If detected, these waves would be a smoking gun for inflation, providing definitive evidence that the universe underwent a period of rapid expansion shortly after the Big Bang. The search for primordial gravitational waves is one of the most exciting frontiers in cosmology, as it holds the potential to unlock a new window into the very first moments of the universe. These waves, if they exist, would carry information about the energy scale of inflation, potentially revealing new physics at energy levels far beyond what can be achieved in particle accelerators. In addition to gravitational waves, there are other potential signatures of inflation that scientists are searching for. One possibility is the existence of topological defects, exotic structures in spacetime that could have formed during inflation. These defects, such as cosmic strings or domain walls, would be relics of the universe's earliest moments and could provide clues about the underlying physics of inflation. While there is currently no direct evidence for topological defects, their existence is predicted by certain inflationary models, and they remain an active area of research. If such defects were detected, they would provide valuable insights into the symmetry-breaking processes that occurred during inflation and could shed light on the fundamental forces that govern the universe. As our understanding of inflation and the early universe continues to evolve, new questions and mysteries emerge. For example, what happens at the very beginning of inflation? The theory of inflation explains the rapid expansion of the universe, but it does not provide a complete picture of what came before inflation or how inflation itself was triggered. This leads us to the question of the initial singularity, the point in time when the universe's density and temperature were thought to be infinite. The standard Big Bang model posits that the universe began from a singularity, a point of infinite density and temperature where the laws of physics break down. However, many physicists believe that the singularity is not a physical reality, but rather a limitation of our current understanding of gravity and quantum mechanics. In this view, the singularity represents a breakdown in our mathematical models, not an actual state of the universe. One possible solution to the singularity problem is the idea of a quantum bounce. In some models of quantum gravity, the universe could have undergone a contraction phase before inflation, reaching a minimum size before bouncing back and expanding again. This would eliminate the need for a singularity and provide a more complete picture of the universe's origins. While this idea is still speculative, it offers a potential way to reconcile the apparent conflict between general relativity and quantum mechanics in the context of the early universe. Another intriguing possibility is that the universe had no beginning at all. In some models of eternal inflation, the universe has always existed in one form or another, with inflation occurring in different regions of spacetime at different times. In this scenario, there is no initial singularity or first moment of creation, Instead, the universe is part of an infinite and eternal multiverse. This idea challenges our conventional notions of time and causality, but it is a serious contender in the realm of theoretical cosmology. Ultimately, the mysteries of cosmic inflation and the shape of the universe are far from fully understood, and they continue to push the boundaries of human knowledge and imagination. As we develop more advanced observational tools and refine our theoretical models, we may come closer to answering some of the most profound questions about the origins and structure of the cosmos. But for now, the universe remains a place of wonder and mystery, filled with unanswered questions that beckon us to explore further. The search for a deeper understanding of the universe's origins is not just a scientific endeavor but a philosophical one as well. It forces us to confront the limits of our knowledge, to grapple with concepts that challenge our intuition, and to ask questions that may never have definitive answers. In this sense, the study of cosmic inflation and the shape of the universe is a journey into the unknown, a quest to unravel the deepest mysteries of existence itself. As we continue to explore the cosmos, we may one day unlock the secrets of inflation, the multiverse, and the true shape of the universe. But until then, the mysteries of space will continue to inspire wonder and curiosity, reminding us of the vastness of the unknown and the beauty of the journey toward understanding. In continuing this journey of exploring cosmic inflation and the shape of the universe, we venture deeper into the realm of unanswered questions, where the very fabric of space-time itself becomes the stage for phenomena that are as mind-boggling as they are awe-inspiring. As we have seen, inflation not only solves some of the puzzles of the early universe but also raises new mysteries about the fundamental nature of reality. These mysteries, when viewed through the lens of modern physics, lead us to some of the most profound philosophical questions about our place in the cosmos and the nature of existence. One of the key concepts that cosmic inflation touches on is the shape of the universe. This is not just a question of geometry. It's about how the universe behaves on the largest possible scales. The shape of the universe determines whether space is finite or infinite, how it expands over time, and what the ultimate fate of the cosmos might be. To understand the shape of the universe, cosmologists rely on a combination of theoretical models and observations of the cosmic microwave background, galaxy distributions, and large-scale structures. When scientists talk about the shape of the universe, they are referring to its curvature, which can be positive, negative, or flat. A universe with positive curvature would be shaped like a sphere, meaning that if you traveled far enough in one direction, you would eventually return to your starting point. This is analogous to how you can travel around the surface of the Earth, which is also curved, and eventually end up back where you began. In a positively curved universe, space is finite, but without any boundaries, it wraps around on itself. A universe with negative curvature, on the other hand, would be shaped like a saddle or a hyperbolic surface. In such a universe, parallel lines would eventually diverge, and space would expand indefinitely without wrapping back on itself. A negatively curved universe is infinite in extent, and its geometry leads to some unusual properties, such as the ability to see farther in certain directions than others, due to the way light would travel in a negatively curved spacetime. Finally, there is the possibility that the universe is flat, meaning that its curvature is zero. In a flat universe, space behaves according to the familiar rules of Euclidean geometry. Parallel lines never meet, and the angles of a triangle add up to 180 degrees. A flat universe can be either finite or infinite, depending on other factors, but in most models, a flat universe implies an infinite expanse of space. Observations from the cosmic microwave background and large-scale structure surveys suggest that the universe is very close to flat, though there is still some uncertainty about its exact curvature. The discovery that the universe appears to be flat is a triumph for the theory of cosmic inflation. One of the key predictions of inflation is that the rapid expansion of space would have stretched the universe to such an extent that any initial curvature would be smoothed out, making the universe appear flat on large scales. This is similar to how a balloon becomes flatter as it is inflated. While the balloon is still curved, the larger it gets, the less noticeable the curvature becomes. However, even if the universe appears flat on the largest scales we can observe, this does not necessarily mean that it is perfectly flat or that it was always flat. The universe could have a very slight curvature that we are unable to detect with current instruments. Additionally, the universe might have undergone different phases of expansion in its early history, leading to regions with varying degrees of curvature. In this sense, the apparent flatness of the universe may be a local property, not a fundamental feature of the entire cosmos. The question of whether the universe is finite or infinite is closely related to its shape. If the universe has positive curvature, it is finite, but without boundaries. If the universe is flat or has negative curvature, it could be infinite in extent. The idea of an infinite universe is both intriguing and challenging to comprehend. In an infinite universe, there would be an infinite number of galaxies, stars, and planets, and possibly even an infinite number of copies of ourselves scattered across the cosmos. Every possible arrangement of matter could exist somewhere in an infinite universe, raising mind-boggling questions about the nature of reality and the limits of human understanding. But how can we know if the universe is truly infinite? The observable universe, the portion of the cosmos we can see, has a finite size due to the finite speed of light and the age of the universe. Beyond the observable universe, there may be regions of space that are forever beyond our reach, either because they are too far away for light to have reached us or because they are receding from us faster than the speed of light due to the universe's expansion. This means that, even if the universe is infinite, we can never directly observe its full extent, leaving the question of its true size open to speculation. The shape of the universe also plays a crucial role in determining its ultimate fate. In a universe with positive curvature, gravity could eventually cause the expansion to slow down and reverse, leading to a big crunch, where the universe collapses back in on itself. This scenario is analogous to a ball thrown into the air that eventually slows down, stops, and falls back to the ground. A positively curved universe is finite and closed, meaning that it has a definite beginning and an eventual end. In a negatively curved or flat universe, however, the expansion could continue forever. In these cases, the universe would be infinite in extent and would keep expanding, potentially leading to a big freeze, where galaxies drift farther and farther apart, stars burn out, and the universe becomes a cold, dark, and empty place. This is the fate predicted by the Standard Model of Cosmology, which suggests that the universe will continue expanding indefinitely due to the influence of dark energy. Dark energy, which makes up roughly 68% of the total energy density of the universe, is a mysterious force that is driving the accelerated expansion of the cosmos. Unlike gravity, which pulls objects together, dark energy causes space to expand at an ever-increasing rate. The nature of dark energy is one of the biggest mysteries in modern cosmology, and understanding it could shed light on the ultimate fate of the universe. One of the most intriguing possibilities is that dark energy is related to the vacuum energy of empty space. According to quantum field theory, even empty space is not truly empty but is filled with virtual particles that constantly pop in and out of existence. This vacuum energy could act as a form of dark energy, driving the accelerated expansion of the universe. However, the theoretical predictions for the vacuum energy are vastly larger than the observed value of dark energy, leading to what is known as the cosmological constant problem, one of the most puzzling issues in modern physics. Another possibility is that dark energy is a dynamic field that changes over time. This idea is known as quintessence, and suggests that the properties of dark energy could evolve as the universe expands. If dark energy is not constant but varies with time, it could lead to different scenarios for the future of the universe. For example, if dark energy becomes stronger over time, it could eventually tear the universe apart in a Big Rip scenario, where galaxies, stars, planets, and even atoms are torn apart by the accelerating expansion of space. The discovery of dark energy has revolutionized our understanding of the universe, but it has also deepened the mystery of its ultimate fate. Will the universe continue expanding forever, or will it eventually collapse in on itself? Will dark energy remain constant, or will it change over time, leading to new and unexpected outcomes? These questions remain at the forefront of cosmological research, and their answers could have profound implications for our understanding of the cosmos and our place within it. As we continue to explore the mysteries of cosmic inflation and the shape of the universe, we are reminded of how much we have yet to learn. The universe, in all its vastness and complexity, continues to surprise us with new discoveries and deeper mysteries. Whether we are pondering the origins of the universe, the nature of dark energy, or the possibility of a multiverse, we are constantly pushed to expand our understanding and challenge our assumptions about the nature of reality. The study of cosmic inflation and the shape of the universe is not just about solving equations or making observations. It is about confronting the deepest questions of existence. What is the nature of space and time? How did the universe come to be? What is the ultimate fate of the cosmos? These are questions that have fascinated humans for millennia, and they continue to drive our quest for knowledge and understanding. As we look to the future, the mysteries of space will undoubtedly continue to captivate our imagination and push the boundaries of what we know. With each new discovery, we come one step closer to unraveling the secrets of the universe. But we are also reminded of how much more there is to explore. The cosmos is vast, and its mysteries are many, but it is this very sense of wonder and curiosity that drives us to keep exploring, to keep asking questions, and to keep searching for answers. The mystery of cosmic inflation and the shape of the universe continues to unfold as we look further into the implications of these phenomena on the grand scale of the cosmos. The vastness of the universe, combined with the intricacies of inflation theory, offers a multitude of potential scenarios for how the universe came to be and what its future might hold. As we peel back the layers of what we understand about inflation, space, and time, we are drawn into deeper mysteries that challenge not just our scientific knowledge, but our very understanding of reality. One of the most striking aspects of cosmic inflation is its potential role in creating the vast structures of the universe that we observe today. When we look out into the night sky, the stars and galaxies we see are not evenly distributed. They are organized into vast clusters, superclusters, and filaments that stretch across the universe. These structures are thought to have formed from tiny quantum fluctuations that were stretched to cosmic scales during the inflationary period. Essentially, the seeds of galaxies and galaxy clusters were planted during the first moments of the universe's existence, during the inflationary era when space expanded at an exponential rate. These quantum fluctuations, random, minuscule changes in the energy field that drove inflation, were stretched across the universe as space itself expanded. Over time, these fluctuations grew and formed regions of slightly higher and lower density in the early universe. The regions of higher density would eventually collapse under the force of gravity, forming the stars, galaxies, and galaxy clusters we observe today. In this sense, cosmic inflation provides a mechanism for explaining how the universe transitioned from a nearly uniform state to the complex, structured cosmos we now inhabit. The idea that the large-scale structure of the universe arose from quantum fluctuations is one of the most profound insights of modern cosmology. It links the smallest scales of quantum mechanics with the largest scales of the cosmos, suggesting that the same laws of physics that govern the behavior of subatomic particles also govern the formation of galaxies and galaxy clusters. This connection between the quantum and the cosmic is a hallmark of inflationary theory and highlights the deep unity of the physical laws that govern our universe. But while inflation theory provides a compelling explanation for the origin of large-scale structure, it also raises new questions about the nature of the universe on even larger scales. One of the most intriguing possibilities is that cosmic inflation may not have been a one-time event confined to the early moments of our universe. Instead, inflation could be an ongoing process that occurs in different regions of space, leading to the creation of multiple universes, what is often referred to as the multiverse. In the multiverse scenario, different regions of space undergo inflation at different rates, with some regions inflating rapidly while others slow down or stop. Each of these regions could represent a separate, bubble, universe with its own distinct properties, such as different physical constants, dimensions, or even different laws of physics. Our universe, according to this view, would be just one of many such bubble universes that were spawned by the inflationary process. This idea of a multiverse is both tantalizing and controversial. On the one hand, it provides a natural explanation for many of the puzzling features of our universe, such as why the physical constants appear to be finely tuned for life. If there are many universes, each with different properties, it is not surprising that we find ourselves in a universe that is conducive to life. We simply happen to inhabit one of the universes where the conditions are right. This is often referred to as the anthropic principle, which suggests that the universe must have the properties it does in order to support the existence of observers like us. On the other hand, the multiverse hypothesis raises profound philosophical and scientific questions. If there are other universes beyond our own, how could we ever observe or interact with them? By definition, these other universes would be outside our observable horizon, meaning that we could never directly detect them. This makes the multiverse a difficult concept to test scientifically, leading some critics to argue that it lies outside the realm of empirical science. Despite these challenges, the multiverse remains a compelling idea that continues to generate debate and exploration within the scientific community. As we contemplate the possibility of a multiverse, we are also led to reconsider the shape and structure of our own universe. If inflation is responsible for creating multiple bubble universes, then what does that say about the shape of the larger cosmos that contains them all? Could the multiverse itself have a shape, or is it an infinite, boundless expanse that defies traditional geometric descriptions? The concept of the shape of the universe becomes even more complex when we consider the possibility of higher dimensions. In our everyday experience, we are familiar with three spatial dimensions: length, width, and height, along with the dimension of time. However, many theories in modern physics, such as string theory, suggest that there could be additional spatial dimensions beyond the three we experience. These extra dimensions could be compactified, meaning that they are curled up so tightly that they are imperceptible to us, or they could be extended in ways that affect the overall geometry of the universe. In the context of inflation and the multiverse, higher dimensions could play a crucial role in shaping the behavior of the cosmos. Some theories suggest that inflation might have occurred not just in three-dimensional space but in higher dimensional space, with different regions of space experiencing different rates of inflation depending on the number of dimensions they inhabit. In such a scenario, the shape of the universe could be much more complex than we can currently imagine, with higher dimensional geometries influencing the behavior of space, time, and matter on both small and large scales. Moreover, if higher dimensions exist, they could provide a natural explanation for some of the mysteries of cosmology, such as the nature of dark matter and dark energy. Dark matter, which makes up about 27% of the universe's mass energy content, and dark energy, which accounts for about 68%, remain two of the most enigmatic substances in the universe. While we can observe their effects on galaxies and the expansion of the universe, their true nature remains elusive. One possibility is that dark matter and dark energy are manifestations of higher dimensional physics. For example, dark matter could consist of particles that exist in higher dimensions but interact with our three-dimensional universe only through gravity. Similarly, dark energy could be the result of the geometry of higher dimensional space affecting the expansion of our universe. These ideas are speculative but represent exciting possibilities for understanding some of the deepest mysteries of the cosmos. The concept of higher dimensions also ties into another profound mystery of the universe: the question of time. Time, as we experience it, appears to flow in one direction, from past to future. But the laws of physics, particularly those of quantum mechanics and general relativity, do not seem to prefer any particular direction for time. This raises the question of why time flows in the way that it does and whether this flow is an intrinsic property of the universe or an artifact of our perception. Inflation may provide some insights into the nature of time. During the inflationary period, space expanded so rapidly that the usual notions of time and causality may have broken down. In this sense, the inflationary epoch represents a kind of reset for the universe, where the arrow of time was set in motion by the end of inflation and the subsequent expansion of space. Some physicists have even speculated that time, as we experience it, could be an emergent property of the universe rather than a fundamental aspect of reality. This idea of emergent time ties into the larger question of the ultimate nature of space and time. Are space and time fundamental building blocks of the universe, or are they the result of deeper, underlying processes that we have yet to fully understand? Some theories, such as quantum gravity and string theory, suggest that space and time may emerge from more fundamental structures, such as networks of quantum information or strings vibrating in higher dimensional space. If space and time are indeed emergent phenomena, then inflation may represent a key moment in the emergence of the universe as we know it. The rapid expansion of space during inflation could be seen as the process by which space and time unfolded from these deeper structures, creating the stage on which the subsequent evolution of the universe would take place. This perspective challenges our traditional understanding of the universe as a fixed backdrop for physical events and suggests that space and time themselves are dynamic, evolving entities. As we continue to probe the mysteries of cosmic inflation and the shape of the universe, we are confronted with more questions than answers. Yet it is precisely this sense of mystery and wonder that drives scientific inquiry. Each new discovery opens up new avenues of exploration, revealing deeper layers of complexity and beauty in the cosmos. The universe, in all its vastness and intricacy, is a testament to the power of human curiosity and imagination. From the quantum fluctuations that gave rise to galaxies, to the potential existence of a multiverse, to the possibility of higher dimensions and emergent spacetime, the study of cosmology challenges us to think beyond the limits of our everyday experience and to grapple with the fundamental nature of reality. In many ways, the study of the universe is as much a philosophical endeavor as it is a scientific one. It forces us to confront questions about the nature of existence, the meaning of life, and our place in the cosmos. Are we alone in the universe, or are there other forms of life in distant galaxies or parallel universes? What is the ultimate fate of the cosmos, and how does it relate to our own lives and experiences? These are questions that have been asked by philosophers, theologians, and scientists for centuries, and they continue to inspire wonder and contemplation today. As we dive deeper into the mysteries of cosmic inflation and the shape of the universe, one of the most intriguing questions revolves around how these concepts relate to the very fabric of existence. Inflation not only shaped the universe we see today but may also hold the key to understanding some of the most profound and perplexing questions in physics, such as the ultimate fate of the cosmos, the nature of dark energy, and the possibility of multiple dimensions or even parallel universes. At its core, inflation is an attempt to explain how the universe could have achieved its current level of homogeneity and isotropy. The fact that, on large scales, the universe looks the same in every direction. Prior to the introduction of inflationary theory, one of the major puzzles in cosmology was the so-called horizon problem. This problem arose from the observation that distant regions of the universe, which are separated by vast distances, appear to have nearly identical temperatures and densities, even though they should not have had enough time to come into thermal equilibrium in the time since the Big Bang. In other words, if you look in opposite directions in the sky, the cosmic microwave background CMB radiation, the afterglow of the Big Bang, looks remarkably similar, even though the regions of space that emitted this radiation should not have been able to communicate with each other, as they are too far apart. Without some kind of mechanism to explain this, it would seem that the universe began with an unexplained level of fine-tuning in its initial conditions. Cosmic inflation provides a solution to this conundrum by positing that, in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. During this brief period, the universe expanded so rapidly that regions of space that were once in close contact were stretched far apart. Before inflation, the universe would have been small enough for all regions to come into thermal equilibrium, meaning that distant parts of the universe could have shared information and equalized their properties. Inflation then rapidly expanded these regions, creating the large, smooth, and isotropic universe we see today. This insight has profound implications not only for our understanding of the early universe but also for the future of cosmology. It suggests that the structure and evolution of the universe are deeply connected to the underlying physics of inflation, and that by studying inflation, we can gain insights into the fundamental laws of nature. One of the key predictions of inflationary theory is that the universe should be spatially flat, meaning that the geometry of space on large scales should be Euclidean. In simple terms, this means that if you were to draw a giant triangle in space, the sum of the angles should add up to 180 degrees, just as it would in a flat, two-dimensional plane. This prediction has been confirmed by observations of the cosmic microwave background, which show that the universe is very close to flat, with only a tiny margin of error. The flatness of the universe is another major success of inflationary theory, as it resolves what is known as the flatness problem. Without inflation, the universe would need to have started off with an extremely fine-tuned set of initial conditions in order to maintain its flatness over time. Even a slight deviation from flatness in the early universe would have led to a vastly different cosmos, one that either collapsed back in on itself shortly after the Big Bang, if it were positively curved like a sphere, or expanded too rapidly for galaxies to form, if it were negatively curved like a saddle. Inflation explains why the universe appears to be so flat today by showing that even a universe that began with a slight curvature would have been stretched flat by the rapid expansion of space. However, the concept of a flat universe does not necessarily imply that the universe is infinite. It is possible for the universe to be both flat and finite, much like the surface of a piece of paper that is rolled into a cylinder. In such a scenario, the universe could have a finite volume while still being flat on large scales. Alternatively, the universe could be truly infinite, stretching out in all directions without end. The true size and shape of the universe remain open questions, and future observations may help shed light on these mysteries. In addition to solving the horizon and flatness problems, inflation also provides a natural explanation for the origin of the tiny fluctuations in density that later gave rise to galaxies and large-scale structures. These fluctuations are thought to have been generated by quantum effects during the inflationary period. As space expanded rapidly, quantum fluctuations in the energy field that drove inflation were stretched across the universe, creating small differences in density that would later grow into the vast cosmic structures we observe today. The study of these primordial fluctuations has become a major focus of modern cosmology, as they contain valuable information about the physics of the early universe. By analyzing the patterns of fluctuations in the cosmic microwave background, scientists can probe the conditions that existed just fractions of a second after the Big Bang. These observations provide strong support for the inflationary model and have helped refine our understanding of how inflation occurred. Despite its successes, inflation theory is not without its challenges and open questions. One of the most significant of these is the so-called inflationary multiverse hypothesis, which arises from certain versions of inflation theory that suggest inflation may not have stopped everywhere in the universe. Instead, it could be that inflation continues in some regions of space while stopping in others, creating a vast multiverse in which different regions of space, each representing a different bubble universe, could have different physical properties. In this scenario, our observable universe would be just one of many such bubbles, each with its own distinct laws of physics and constants of nature. Some regions of the multiverse might have very different properties from our own, with different strengths of gravity, different numbers of dimensions, or even entirely different fundamental forces. The idea of a multiverse is a radical departure from the traditional view of the universe as a single, self-contained entity, and it raises profound questions about the nature of reality and our place within it. One of the key implications of the multiverse hypothesis is that it provides a possible explanation for why our universe appears to be so finely tuned for life. In recent decades, scientists have discovered that many of the fundamental constants of nature, such as the strength of the electromagnetic force, the mass of the electron, and the cosmological constant that governs the expansion of the universe, appear to be precisely calibrated to allow for the existence of life as we know it. Even small changes in these constants would render the universe uninhabitable, raising the question of why they have the values they do. In a multiverse, this apparent fine-tuning could be explained by the fact that different regions of the multiverse have different physical properties. We find ourselves in a universe that is suitable for life simply because it is one of the rare regions where the conditions are right. In other words, if there are many universes with different properties, it is not surprising that we happen to live in one where the physical constants are conducive to life. This idea is sometimes referred to as the anthropic principle, which suggests that the universe must have the properties it does in order to support observers like us. While the multiverse hypothesis is an intriguing and potentially powerful explanation for the fine-tuning of the universe, it also presents significant challenges. One of the most important of these is the question of whether the multiverse can ever be tested or observed. By definition, the other bubble universes in the multiverse would be beyond the reach of our telescopes, making direct observation impossible. Some critics argue that this makes the multiverse a scientifically untestable idea, and therefore not a valid scientific hypothesis. Despite these challenges, the multiverse remains a popular and actively researched idea in theoretical physics. Some scientists hope that indirect evidence for the multiverse could be found by studying the fine details of cosmic inflation, or by looking for subtle signatures in the cosmic microwave background that might indicate the presence of other universes. Others are exploring the possibility that the multiverse could be connected to ideas from string theory, quantum gravity, or other areas of fundamental physics. Another major question that arises from inflationary theory is the nature of dark energy, the mysterious force that is driving the accelerated expansion of the universe. Dark energy is thought to make up about 68% of the total energy density of the universe, yet its true nature remains one of the biggest unsolved mysteries in cosmology. Some scientists have suggested that dark energy could be related to the energy field that drove inflation, meaning that the same force that caused the rapid expansion of the early universe might still be at work today, driving the accelerated expansion we observe on large scales. The relationship between inflation and dark energy is one of the most intriguing areas of current research. While inflation is thought to have occurred during the earliest moments of the universe's existence, dark energy appears to be a present-day phenomenon, dominating the universe's energy budget and causing its accelerated expansion. Some theories propose that dark energy might be a remnant of the inflationary energy field, albeit operating at a much lower intensity than during the early moments of cosmic inflation. This idea could unify our understanding of the forces that shaped the universe at both its birth and its current phase. The discovery that the universe's expansion is accelerating, which was made in the late 1990s through observations of distant supernovae, was a revolutionary moment in cosmology. Prior to this, scientists had assumed that the expansion of the universe, which began with the Big Bang, would gradually slow down over time due to the gravitational attraction of matter. However, the observation of these supernovae revealed that not only is the universe continuing to expand, but the rate of expansion is actually increasing. This suggests the existence of a mysterious force, dark energy, that is pushing galaxies apart and overpowering the effects of gravity. One of the most confounding aspects of dark energy is that it appears to be distributed uniformly throughout space, with the same density everywhere in the universe. This is very different from ordinary matter, which clumps together to form stars, galaxies, and other structures. Dark energy's uniformity suggests that it may be related to the vacuum energy of space itself, sometimes referred to as the cosmological constant, a term originally introduced by Albert Einstein in his equations for general relativity. In Einstein's time, the cosmological constant was thought to be a kind of anti-gravity force that would prevent the universe from collapsing under its own gravity. Einstein later abandoned the idea when it became clear that the universe was expanding, but it was revived in the late 20th century to explain the accelerating expansion of the universe. The cosmological constant is now one of the leading explanations for dark energy, though its true nature remains elusive. The connection between inflation and dark energy raises another profound question about the fate of the universe. If dark energy continues to dominate the universe's expansion, it could lead to a future in which the universe expands forever, becoming increasingly cold, dark, and empty. This scenario, sometimes referred to as the Big Freeze, suggests that over trillions of years, galaxies will move further and further apart, stars will burn out, and the universe will eventually become a vast, dark, and desolate expanse. The accelerated expansion driven by dark energy could even reach a point where not only galaxies but also individual stars and atoms are torn apart in a catastrophic event known as the Big Rip. On the other hand, it is also possible that dark energy could change over time. Some theories suggest that dark energy might decay or reverse its effects, leading to a future in which the universe's expansion slows down or even reverses, resulting in a Big Crunch. In this scenario, the universe would eventually collapse back in on itself, possibly leading to a new Big Bang and the birth of a new universe. While this idea is more speculative, it highlights the profound connections between inflation, dark energy, and the ultimate fate of the cosmos. One of the most exciting developments in modern cosmology is the potential to study inflation, dark energy, and the shape of the universe through new and more advanced observational techniques. The cosmic microwave background (CMB), the faint afterglow of the Big Bang, has already provided crucial insights into the early universe and the inflationary process. Detailed measurements of the CMB by missions like the Wilkinson Microwave Anisotropy Probe (WMAP) and the Planck satellite have confirmed many of the key predictions of inflationary theory, including the flatness of the universe and the presence of primordial fluctuations. However, there are still many unanswered questions that future observations could help resolve. For example, scientists are searching for evidence of gravitational waves from inflation, which would provide a direct link to the physics of the inflationary epoch. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, and they are predicted to have been generated during inflation by the rapid stretching of space. The detection of these primordial gravitational waves would not only confirm inflation but also provide a window into the energy scale at which inflation occurred, offering clues about the underlying physics of the early universe. In addition to studying the CMB, astronomers are using large-scale galaxy surveys to map the distribution of matter in the universe and probe the effects of dark energy. By measuring the distances to millions of galaxies and the patterns of their motion, scientists can trace the history of the universe's expansion and determine how dark energy has influenced the growth of cosmic structures. Projects like the Dark Energy Survey and the upcoming Euclid mission aim to provide more precise measurements of dark energy's properties and its role in the universe's evolution. These observations are also helping to refine our understanding of the shape and geometry of the universe. While current data suggests that the universe is flat on large scales, there is still room for small deviations from flatness. By studying the detailed properties of the CMB and the large-scale structure of the universe, scientists hope to determine whether the universe is perfectly flat or whether it has a slight curvature. Even a small deviation from flatness could have profound implications for our understanding of the universe's origin and its ultimate fate. One of the most intriguing possibilities is that the universe may be finite but unbounded, meaning that it has a finite volume but no edges or boundaries. This idea is often compared to the surface of a sphere, which is finite in area but has no boundaries. In a similar way, the universe could be curved in such a way that if you traveled far enough in one direction, you would eventually return to your starting point, much like how traveling around the Earth brings you back to your original location. This possibility is still speculative, but it is an active area of research, and future observations may provide more clues about the true shape of the universe. As we continue to explore the mysteries of cosmic inflation, dark energy, and the shape of the universe, we are constantly reminded of how little we truly know about the cosmos. These questions touch on some of the deepest and most profound mysteries in all of science. Questions about the nature of space and time, the origin of the universe, and the forces that govern its evolution. The answers to these questions may not only reshape our understanding of the universe but also our place within it. At the same time, the study of inflation and dark energy raises philosophical questions about the nature of reality itself. If the multiverse hypothesis is correct, and our universe is just one of many, then we may need to rethink our understanding of what it means to live in a universe. The idea of parallel universes, each with its own distinct properties and laws of physics, challenges our most fundamental assumptions about the nature of existence and the uniqueness of our own universe. In many ways, the study of the universe is also a study of our own limitations as observers. The vastness of the cosmos, the incomprehensible scales of time and space, and the mysteries of dark energy and inflation remind us that we are tiny, fragile beings living in a universe that is far larger and more complex than we can fully grasp. Yet, despite these challenges, we continue to push the boundaries of knowledge, using our tools and technologies to probe the deepest mysteries of the cosmos. The exploration of cosmic inflation and the shape of the universe is far from over. New discoveries are being made every day, and with each new piece of data, we move one step closer to answering the big questions about the origin and evolution of the universe. As we look to the future, it is clear that the study of the cosmos will continue to be a source of wonder, inspiration, and discovery for generations to come. The next frontier in understanding cosmic inflation and the shape of the universe lies in the pursuit of more precise observations and more advanced theoretical models. Cosmologists are working to refine their understanding of the inflationary process itself. One of the key goals is to pinpoint exactly what caused the universe to inflate so rapidly and how that process unfolded. Various models of inflation have been proposed, with each offering a different mechanism to explain this rapid expansion. One of the leading contenders is known as chaotic inflation, which posits that inflation is driven by a scalar field, often referred to as the inflaton, that rolls down a potential energy curve. As this field evolves, it causes the universe to expand rapidly, and as it nears the end of the inflationary process, the energy stored in the inflaton field is converted into the matter and radiation that filled the early universe. This mechanism offers a compelling explanation for the rapid expansion, but there are many different forms that the inflaton potential could take, each leading to slightly different predictions about the universe's structure and evolution. Another approach is called eternal inflation, which suggests that inflation never really ends in certain regions of the universe. In this model, some areas of space undergo inflation indefinitely, while others stop inflating and form pocket universes like our own. This model not only explains the rapid expansion of our own universe but also provides a framework for the multiverse hypothesis. In the eternal inflation scenario, our universe is just one of countless others, each with its own distinct properties and laws of physics. While this idea is speculative, it offers a potential solution to some of the mysteries surrounding the initial conditions of our universe, such as why it appears to be so finely tuned for the existence of life. In parallel with these theoretical developments, there is a growing effort to test inflationary models through observational data. One of the most promising avenues is the study of the cosmic microwave background, CMB, polarization. The CMB contains a wealth of information about the early universe, and its polarization patterns offer clues about the physics of inflation. In particular, scientists are searching for a specific pattern of polarization known as B-mode polarization, which would be a telltale signature of gravitational waves generated during inflation. The detection of B-mode polarization would not only provide direct evidence for inflation but also offer insight into the energy scale at which inflation occurred, helping to narrow down the range of possible inflationary models. In addition to CMB polarization, researchers are also looking at large-scale structure surveys to probe the effects of inflation. These surveys map the distribution of galaxies and other cosmic structures, allowing scientists to study how matter clumped together over time. Inflationary models make specific predictions about the distribution of these structures, and by comparing these predictions to observational data, scientists can test different inflationary scenarios. Projects like the Large Synoptic Survey Telescope, LSST, and the Square Kilometre Array, SKA, are expected to provide unprecedented data on the large-scale structure of the universe, offering new opportunities to study inflation and its effects on the cosmos. The study of inflation also has important implications for our understanding of fundamental physics. Inflationary theory connects the behavior of the universe on the largest scales with the behavior of particles on the smallest scales. This connection suggests that inflation may be linked to theories of quantum gravity, such as string theory or loop quantum gravity. In these theories, spacetime itself is thought to be quantized, meaning that it has a discrete structure at the smallest scales. While we do not yet have a complete theory of quantum gravity, the study of inflation could provide important clues about how spacetime behaves at these scales. One of the key challenges in unifying inflation with quantum gravity is the problem of initial conditions. In most inflationary models, inflation begins when the universe is in a high-energy, chaotic state. However, it is not yet clear what set the stage for inflation to begin. Some researchers have proposed that inflation could be a natural consequence of quantum fluctuations in spacetime, while others suggest that inflation could be connected to the formation of a black hole or some other high-energy event. This is an area of active research, and new insights into the origins of inflation could help bridge the gap between cosmology and fundamental physics. Another exciting area of research is the study of cosmic strings, which are hypothetical one-dimensional defects in spacetime that could have been produced during the inflationary process. Cosmic strings are predicted to form in certain inflationary models and could leave observable imprints on the cosmic microwave background or in the distribution of galaxies. The detection of cosmic strings would provide strong evidence for certain types of inflationary models and offer a new way to probe the physics of the early universe. The shape of the universe is another major question tied to inflation and the overall structure of spacetime. Current observations suggest that the universe is flat on large scales, but this flatness is not guaranteed. It is possible that the universe could have a slight curvature, either positively or negatively, which would affect its overall geometry and evolution. A positively curved universe would be closed, meaning that it would eventually stop expanding and begin to contract, while a negatively curved universe would be open, expanding forever. Inflationary models predict a flat universe, but small deviations from flatness could still exist and may be detectable with more precise observations. The shape of the universe also raises questions about its topology, whether space is simply connected like a flat sheet, or whether it has a more complex structure. In some theories, the universe could be multiply connected, meaning that it loops back on itself in strange ways. For example, if the universe had a toroidal topology, it would be shaped like a three-dimensional donut, with space wrapping around in all directions. In such a universe, if you traveled far enough in one direction, you would eventually return to your starting point. While this idea sounds exotic, it is consistent with general relativity, and there are ongoing efforts to detect signs of such topological features in the cosmic microwave background. As we delve deeper into the mysteries of inflation and the shape of the universe, we are also confronted with philosophical questions about the nature of reality. The multiverse hypothesis, which is a natural consequence of some inflationary models, suggests that our universe is just one of an infinite number of universes, each with its own distinct properties. This idea challenges the traditional view that our universe is the only one and raises questions about the meaning of existence and the nature of physical laws. If there are countless other universes, each with its own laws of physics, what does that say about the universality of the laws we observe in our own universe? The multiverse also raises questions about the nature of scientific inquiry. In a multiverse, many of the properties of our universe, such as the values of fundamental constants, may be determined by chance rather than by any underlying principle. If this is the case, then certain aspects of the universe may be beyond the reach of scientific explanation, as they would be the result of random variation across different universes. This possibility has sparked debate among scientists and philosophers about the limits of scientific knowledge and the role of chance in the cosmos. Despite these challenges, the study of inflation and the shape of the universe offers a window into the deepest mysteries of existence. As we continue to explore these questions, we are constantly reminded of the vastness and complexity of the cosmos, and of our own small place within it. The quest to understand the universe is a journey that has spanned centuries, and it is far from over. With each new discovery, we come closer to unlocking the secrets of the cosmos and understanding our place in the grand tapestry of the universe. As we probe further into the intricate web of cosmic inflation and the shape of the universe, it is essential to appreciate the technological advancements that have made this exploration possible. The development of sophisticated telescopes, satellites, and detection equipment has allowed scientists to observe the universe with unprecedented detail. For instance, the Planck satellite, launched by the European Space Agency in 2009, has provided some of the most precise measurements of the cosmic microwave background radiation to date. The data collected from Planck has significantly advanced our understanding of the early universe, supporting inflationary models and refining our estimates of the universe's age and composition. The field of gravitational wave astronomy has also emerged as a revolutionary frontier in understanding cosmic inflation. Gravitational waves, ripples in spacetime caused by massive accelerating objects, were first detected in 2015 by the LIGO Observatory. These detections opened a new avenue for studying the universe and provided a unique way to probe the inflationary epoch. During inflation, the rapid expansion of the universe could generate gravitational waves, and detecting these waves could provide direct evidence of the inflationary process. Upcoming missions, such as the Laser Interferometer Space Antenna, LISA, aim to explore the gravitational wave spectrum further and search for signatures of inflation. The interplay between inflation and the shape of the universe continues to captivate researchers. As cosmologists work to understand the implications of flatness, they consider how this geometry relates to dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy constitutes about 68% of the total energy density of the universe, yet its nature remains largely unknown. Some theories propose that dark energy may be a remnant of the inflationary phase, linking the early universe's expansion to the current accelerated expansion. This idea hints at a deeper connection between the universe's shape, its inflationary history, and the ongoing dynamics governing its evolution. Moreover, the potential existence of cosmic defects, such as monopoles or strings, adds another layer of complexity to the narrative of cosmic inflation and the shape of the universe. These defects could arise during phase transitions in the early universe and could leave observable signatures on cosmic structure. The search for such defects is ongoing, and their detection could help confirm specific models of inflation, offering further insights into the universe's shape and behavior. As we attempt to visualize the universe's shape, it is important to consider how humans have conceptualized space throughout history. With the advent of modern science, our understanding evolved, leading to the realization that the universe is a three-dimensional expanse shaped by gravitational forces and governed by the principles of general relativity. Today, cosmologists explore various models to understand how the universe could be shaped, whether it is flat, open, or closed, and how this shape influences its fate. Mathematically, cosmologists utilize tools from differential geometry and topology to describe the universe's shape. They model the universe as a manifold, a mathematical structure that can be curved or flat. The Friedmann-Lemaitre-Robertson-Walker (FLRW) metric is often employed to describe a homogeneous and isotropic universe, capturing different curvature scenarios. By analyzing observational data and fitting it to these models, researchers can glean insights into the universe's shape and its implications for cosmological evolution. The implications of these models extend beyond mere geometric considerations. They also inform our understanding of fundamental physics. The nature of spacetime itself, whether it is discrete or continuous, flat or curved, has profound consequences for our understanding of reality. In string theory, for instance, the shape of the universe could influence the fundamental properties of particles and forces. Different compactifications of extra dimensions lead to various physical predictions, suggesting that the geometry of the universe plays a crucial role in determining the laws of physics. As researchers delve into the mathematical frameworks that describe the universe's shape, they also confront the philosophical implications of their findings. The concept of a flat universe, supported by observational evidence, suggests that we live in a spatially infinite cosmos. This notion raises intriguing questions about the nature of infinity, the possibility of multiple copies of ourselves in different regions of space, and the consequences of such a reality for our understanding of individuality and existence. If the universe is infinite and uniform on large scales, it challenges our intuitions about uniqueness and identity, inviting philosophical inquiry into the nature of consciousness and existence itself. Furthermore, as we consider the broader implications of cosmic inflation and the shape of the universe, we must grapple with the significance of our position within this vast cosmic landscape. The anthropic principle suggests that the physical laws and constants we observe are finely tuned to allow for the existence of life. Our universe, with its specific parameters, seems uniquely suited for the emergence of conscious observers. This observation raises profound questions about the role of observers in the universe, suggesting that consciousness itself may play a role in shaping the cosmos we experience. In a universe governed by chance and random variations, the notion that we are here to contemplate our existence becomes an extraordinary phenomenon. The multiverse hypothesis, with its countless variations of universes, reinforces the idea that our particular cosmic conditions are not necessarily inevitable. This realization emphasizes the uniqueness of our universe while inviting us to explore the deeper meaning of existence and the interplay between chance and necessity. As the exploration of cosmic inflation and the shape of the universe continues, researchers are not only expanding our understanding of the cosmos but also deepening our appreciation for the intricate tapestry of existence. Each discovery serves as a reminder of the interconnectedness of all things, from the smallest subatomic particles to the vast cosmic structures that make up the universe. The study of cosmic inflation and the shape of the universe represents one of the most exciting frontiers of modern science. Through a combination of theoretical advancements, observational data, and philosophical inquiry, we are gradually piecing together the puzzle of our existence in a universe that is both grand and mysterious. As we seek to understand the origins, structure, and fate of the cosmos, we are confronted with profound questions about the nature of reality, the limits of human knowledge, and the significance of our place in the grand scheme of things. In this journey, the pursuit of knowledge becomes a transformative endeavor, not only expanding our understanding of the universe but also shaping our perspectives on life, existence, and our role within the cosmos. The mysteries of inflation and the shape of the universe serve as a reminder that while we may have made significant strides in our understanding of the cosmos, there is still so much more to discover. As we continue to explore the frontiers of knowledge, we remain humble in the face of the vast unknown, driven by curiosity and the desire to unlock the secrets of the universe that lie beyond the stars. As we venture deeper into the realms of cosmic inflation and the shape of the universe, we begin to confront not only the scientific challenges but also the profound philosophical questions that arise from our attempts to comprehend the cosmos. The implications of cosmic inflation extend far beyond mere numbers and equations. They prompt us to rethink our place in a universe that is constantly expanding and evolving. One of the most significant consequences of the inflationary model is the idea that our observable universe is just a tiny fraction of the entire cosmos. While we can see a finite portion of the universe, the inflationary scenario suggests that there may be vast regions beyond our reach, perhaps infinitely large, that remain hidden from our observation. This raises the possibility of a multiverse, an ensemble of diverse universes with varying physical laws and constants. In this framework, our universe is but one of countless others, each with its unique characteristics, resulting from different initial conditions during the inflationary epoch. The multiverse hypothesis challenges our traditional notions of scientific inquiry. In a multiverse scenario, the idea of fine-tuning becomes more complex, as the existence of many universes could mean that ours is simply one where the conditions happen to allow for the emergence of life. This challenges the anthropic principle, suggesting that we cannot just rely on observational data from our own universe to infer universal truths. Instead, we must consider a broader context that includes all possible universes, each with its unique set of physical laws. This shift in perspective invites us to rethink the nature of scientific evidence and the criteria we use to evaluate competing theories. In our quest to understand the shape of the universe, we encounter the concept of topology. The topology of the universe refers to its overall structure and the way it is connected. Different topological models can yield various shapes, such as toroidal, donut-shaped, or hyperbolic geometries. Recent observations, particularly from the cosmic microwave background, have provided valuable data that help cosmologists determine the universe's topology. While the prevailing view suggests a flat universe, the possibility of complex topologies remains an intriguing area of research, with implications for how we understand cosmic evolution. The interplay between cosmic inflation, the shape of the universe, and the laws of physics also invites us to explore the fundamental nature of reality. At its core, physics seeks to describe the universe through fundamental forces and particles. However, the origins of these forces remain enigmatic. Inflation suggests a mechanism through which the universe underwent rapid expansion, but what drove this inflationary process? Some theories propose that inflation was driven by a scalar field, often referred to as the inflaton. This hypothetical field would have possessed a high energy density during the early universe, leading to the rapid expansion we associate with inflation. The search for the inflaton and the physics governing inflation has become a central focus of modern cosmology. Different models of inflation predict varying behaviors of the inflaton field, which can leave specific signatures in the cosmic microwave background. By studying these signatures, scientists hope to uncover clues about the physics of the early universe and, potentially, the nature of the inflaton itself. Moreover, the concept of cosmic inflation introduces an element of randomness into the very fabric of the universe. During the inflationary epoch, quantum fluctuations could have given rise to the initial density variations that eventually led to the large-scale structure we observe today. These fluctuations suggest that the universe is inherently stochastic, governed by probabilistic principles that challenge our deterministic understanding of physics. This randomness opens new avenues for exploring the relationship between quantum mechanics and cosmology, leading to potential breakthroughs in our understanding of fundamental physics. The discussion of cosmic inflation and the universe's shape is also closely linked to the question of the universe's fate. While we can describe the universe's current state and its expansion, predicting its future involves navigating complex dynamics. If the universe is flat and dominated by dark energy, it may continue to expand indefinitely, leading to a scenario known as the Big Freeze, where galaxies drift apart and the universe becomes increasingly cold and dark. Alternatively, if the density of matter exceeds a critical threshold, gravitational forces could eventually lead to a Big Crunch, where the universe collapses in on itself. The possibility of a Big Rip, where dark energy accelerates expansion to the point of tearing apart galaxies, stars, and eventually atoms, adds yet another dimension to our understanding of cosmic evolution. The fate of the universe is not merely a theoretical exercise. It has profound implications for our understanding of existence and the future of life itself. As we contemplate the long-term evolution of the cosmos, we are forced to confront our own mortality and the transient nature of existence. The very act of pondering the fate of the universe encourages us to reflect on our place in the grand narrative of cosmic history. In parallel with these scientific inquiries, there is a cultural dimension to our understanding of cosmic inflation and the shape of the universe. Throughout history, humanity has sought to make sense of the cosmos, interpreting its wonders through philosophy. The stories we tell about the universe shape our understanding of reality and our place within it. As we uncover the secrets of the cosmos, we must also acknowledge the cultural narratives that have influenced our interpretations and aspirations. The exploration of cosmic inflation and the shape of the universe continues to inspire a sense of wonder and curiosity. As we unlock the mysteries of the cosmos, we also confront the limits of human understanding. The more we learn about the universe, the more we realize how much remains to be discovered. This paradox of knowledge serves as a reminder that the pursuit of understanding is an endless journey, where each answer gives rise to new questions. As we look to the future, advancements in technology and observational techniques promise to deepen our understanding of cosmic inflation and the universe's shape. The next generation of telescopes, such as the James Webb Space Telescope, will provide unprecedented insights into the early universe, potentially shedding light on the mechanisms of inflation and the formation of cosmic structures. These observations will enhance our ability to test inflationary models and refine our understanding of the fundamental processes that govern the universe's evolution. The journey through cosmic inflation and the shape of the universe is a remarkable testament to human curiosity and ingenuity. As we navigate the complexities of these phenomena, we are not merely seeking answers to scientific questions. We are engaging with the very essence of existence itself. The mysteries of the cosmos challenge us to expand our horizons, both scientifically and philosophically, inviting us to contemplate the nature of reality and our place within it. The exploration of cosmic inflation and the shape of the universe is not just a scientific endeavor. It is a journey that connects us to the cosmos and the stories we tell about it. It reminds us of our shared humanity and our collective quest for understanding in the face of the unknown. As we continue to seek knowledge, we are drawn closer to the mysteries of existence, igniting a spark of curiosity that will propel future generations to explore the cosmos and unlock the secrets that lie beyond the stars. As we forge ahead into the uncharted territories of cosmic inflation and the shape of the universe, we begin to unravel the intricate tapestry of cosmic history and the fundamental principles that govern our reality. The discussion of cosmic inflation is intertwined with the evolution of the universe from its earliest moments, emphasizing the pivotal role that rapid expansion played in shaping the cosmos we observe today. To grasp the significance of cosmic inflation, we must first appreciate the conditions that existed in the early universe. At the moment of the Big Bang, the universe was not only hot and dense but also homogeneous and isotropic, meaning it was nearly the same in all directions. However, this state of uniformity posed a paradox. Observations of the cosmic microwave background radiation reveal slight fluctuations in temperature, indicating that the universe is not perfectly smooth. These variations are essential for the formation of galaxies and large-scale structures, yet their origin remained a mystery. Cosmic inflation, first proposed by physicist Alan Guth in the 1980s, emerged as a compelling solution to this enigma. It posited that the universe underwent an exponential expansion during a fraction of a second after the Big Bang. This rapid growth smoothed out irregularities, ensuring that the observable universe appears homogeneous on large scales. More importantly, inflation provided a mechanism to explain the observed temperature fluctuations in the cosmic microwave background. During inflation, quantum fluctuations in the inflaton field generated small density variations, which eventually grew into the galaxies and clusters we see today. The mathematics behind inflation involves complex field theories and particle physics, drawing upon concepts from quantum mechanics and general relativity. The inflaton field, which drives inflation, is often described by a scalar field, a type of field characterized by a single value at each point in space. The energy associated with this field can change over time, allowing it to create the rapid expansion that defines the inflationary epoch. The specifics of the inflaton's potential energy and its dynamics can vary between different inflationary models, leading to a variety of predictions about the universe's properties. As we analyze the consequences of cosmic inflation, we encounter fascinating implications regarding the geometry and topology of the universe. Observations suggest that the universe is flat on large scales, meaning that parallel lines will never converge or diverge, akin to Euclidean geometry. This flatness can be interpreted through the lens of cosmic inflation, as rapid expansion stretches out the fabric of spacetime, making any initial curvature negligible. However, the question of whether the universe is globally flat or possesses more intricate topology remains open to exploration. The shape of the universe is a topic of profound significance that extends beyond geometry. It shapes our understanding of the cosmos and our place within it. Different models propose various geometrical configurations for the universe, such as spherical, hyperbolic, or flat geometries. Each of these shapes influences cosmic evolution, the distribution of galaxies, and the behavior of light traveling through space. For instance, in a positively curved universe, light rays would eventually converge, while in a negatively curved universe, they would diverge. These distinctions carry important implications for our understanding of cosmic structures and the propagation of light. To unravel these mysteries, scientists employ advanced observational techniques and analytical tools. Projects such as the Planck satellite mission have provided detailed maps of the cosmic microwave background, allowing researchers to scrutinize the universe's geometry and detect subtle fluctuations. These observations are instrumental in testing different inflationary models and refining our understanding of the underlying physics. In recent years, the exploration of dark energy has also become central to discussions of cosmic inflation and the shape of the universe. Dark energy, the enigmatic force driving the universe's accelerated expansion, is believed to constitute a significant portion of the universe's total energy density. Understanding its nature and how it relates to inflation is one of the key challenges facing modern cosmology. Some theories posit that dark energy could be linked to the inflaton field, suggesting a continuity between the early universe's rapid expansion and the present-day acceleration of cosmic expansion. The implications of cosmic inflation and the shape of the universe extend beyond mere mathematical models. They challenge our fundamental assumptions about reality and our place within it. The idea that our universe may be just one among countless others invites us to contemplate our existence in a broader context. It raises profound questions about the nature of life, consciousness, and the universe's purpose, compelling us to engage with philosophical inquiries that transcend scientific boundaries. As we explore these ideas, it becomes clear that the interplay between scientific inquiry and philosophical reflection is essential for a comprehensive understanding of cosmic inflation and the shape of the universe. The pursuit of knowledge is not solely about gathering data or formulating theories. It is also a deeply human endeavor that reflects our innate curiosity and desire to make sense of the universe. Furthermore, the advances in technology and observational capabilities promise to unveil new insights into cosmic inflation and the universe's shape. Upcoming missions, such as the European Space Agency's Euclid satellite and NASA's Roman Space Telescope, are poised to revolutionize our understanding of dark energy and cosmic structure. By mapping the distribution of galaxies and studying the cosmic microwave background with unprecedented precision, these missions will help test existing theories and pave the way for new paradigms in cosmology. In contemplating the mysteries of cosmic inflation and the shape of the universe, we are continually reminded of the interconnectedness of science, philosophy, and the human experience. The cosmos invites us to ask questions, to explore the unknown, and to embrace the complexities of existence. As we stand on the brink of new discoveries, we are also challenged to reflect on the broader implications of our findings and the stories we choose to tell about the universe. Ultimately, the exploration of cosmic inflation and the shape of the universe serves as a reminder of the wonders that await us in the cosmos. Each discovery not only expands our knowledge but also deepens our appreciation for the intricate dance of forces and particles that govern our reality. The pursuit of understanding is a journey that transcends time and space, uniting us in our quest for knowledge and the mysteries that lie beyond the stars. As we continue to probe the depths of cosmic inflation and the universe's shape, we embrace the uncertainty and complexity of the universe. We are driven by an unyielding curiosity to uncover the secrets of existence, to explore the interplay of light and dark, and to seek meaning in a vast and enigmatic cosmos. The mysteries of the universe are not merely scientific puzzles to be solved. They are invitations to ponder our existence, to connect with the universe's grandeur, and to recognize our role within the cosmic narrative. In this ongoing quest for understanding, we acknowledge that the universe is a vast, interconnected web of possibilities. Each new insight opens doors to further exploration, reminding us that the pursuit of knowledge is a journey without end. The legacy of cosmic inflation and the shape of the universe will inspire future generations of scientists, philosophers, and curious minds, fostering a spirit of inquiry that transcends disciplinary boundaries. As we conclude this exploration of cosmic inflation and the shape of the universe, we are left with a sense of awe and wonder. The mysteries of the cosmos beckon us to continue our quest for understanding, to seek out new horizons, and to embrace the beauty of the unknown. In this journey, we find not only answers but also new questions, inviting us to delve deeper into the cosmic enigma that defines our existence. As we reflect on the profound implications of cosmic inflation and the shape of the universe, we are reminded that our understanding is continually evolving. The interplay between observation, theory, and philosophical inquiry will shape the future of cosmology, guiding us toward new insights and discoveries. The universe is a tapestry woven from the threads of knowledge and curiosity, and as we navigate its complexities, we honor the legacy of those who have come before us while inspiring those who will follow. The exploration of cosmic inflation and the shape of the universe is a testament to the human spirit's enduring quest for knowledge. It invites us to transcend the boundaries of our understanding, to contemplate the mysteries of existence, and to embrace the interconnectedness of all things. As we gaze into the cosmos, we find not only the answers we seek but also the profound questions that will continue to drive our exploration of the universe for generations to come. As we delve deeper into the enigmatic realms of cosmic inflation and the shape of the universe, we find ourselves at the intersection of various scientific disciplines, each contributing unique perspectives and insights into these profound questions. The interplay between cosmology, physics, and philosophy shapes our understanding of the universe and challenges us to contemplate the nature of existence itself. At the heart of cosmic inflation lies the concept of the inflaton field, a hypothetical scalar field that is responsible for the rapid expansion of the universe in its earliest moments. This field is not merely a mathematical construct. It embodies the energy dynamics of the early universe and influences the subsequent evolution of cosmic structures. The exact nature of the inflaton remains one of the outstanding questions in modern physics. Various models propose different types of inflatons, ranging from simple scalar fields to more complex entities that incorporate aspects of particle physics. One prominent model of inflation is the slow-roll inflation scenario, where the inflaton field gradually rolls down its potential energy landscape. This slow descent allows for a prolonged period of inflation, smoothing out any initial irregularities in the universe's fabric. The potential energy associated with the inflaton field drives the expansion, while the kinetic energy diminishes, leading to a stable state where inflation can occur for an extended duration. This model successfully explains many features of the cosmic microwave background, including the observed uniformity and fluctuations. In contrast, other models suggest a more dynamic approach to inflation. The new inflation model proposes that the inflaton field can oscillate rapidly, leading to varying rates of expansion. These oscillations create a more complex structure of density variations in the early universe, ultimately influencing the formation of galaxies and large-scale cosmic structures. Such models emphasize the intricate relationships between the inflaton, energy densities, and the geometry of spacetime. The implications of these inflationary models extend far beyond theoretical physics. They touch upon the very nature of reality and our understanding of the universe. If the inflaton field existed in the early universe, it raises profound questions about the existence of other scalar fields, the nature of vacuum energy, and the possibility of multiple inflationary phases. The concept of eternal inflation, in particular, posits that inflation can occur in isolated regions of spacetime, leading to a multiverse where countless universes coexist, each with its unique physical properties. This idea challenges our traditional notions of a singular, coherent universe and opens the door to a more complex and interconnected cosmic reality. As we continue to explore cosmic inflation, it is essential to consider its impact on the overall structure of the universe. The inflationary epoch not only reshaped the universe but also left a lasting imprint on its geometry. Observations of the cosmic microwave background reveal that the universe is flat on large scales, supporting the predictions of inflationary models. However, the exact shape of the universe, whether it is globally flat, closed, or open, remains a subject of active investigation. The geometry of the universe is determined by its total energy density, including contributions from matter, radiation, and dark energy. The critical density, which serves as a threshold for determining the universe's geometry, can be expressed in terms of the density parameter, denoted by omega. If omega is equal to 1, the universe is flat. If omega is greater than 1, the universe is closed. And if omega is less than 1, the universe is open. Current observations suggest that the universe is remarkably close to flat, indicating that its geometry is finely tuned to maintain a delicate balance between gravitational forces and cosmic expansion. To investigate the shape of the universe, scientists utilize advanced observational techniques, including large-scale galaxy surveys and measurements of the cosmic microwave background. The Planck satellite mission, which mapped the cosmic microwave background with exceptional precision, provided invaluable data for cosmologists to analyze. By examining the patterns of temperature fluctuations and the distribution of galaxies, researchers can glean insights into the universe's geometry and test various cosmological models. The exploration of cosmic inflation and the shape of the universe also invites us to confront fundamental philosophical questions about existence and reality. The possibility of a multiverse challenges our understanding of causality, determinism, and the nature of choice. If our universe is but one of countless others, how do we ascribe meaning to our existence? This philosophical inquiry is not merely an abstract exercise. It resonates deeply with our quest for understanding and connection in a seemingly indifferent cosmos. Moreover, the implications of cosmic inflation extend to the study of dark energy, which is believed to be driving the accelerated expansion of the universe. Dark energy constitutes a significant portion of the universe's total energy density, yet its nature remains elusive. Some theories suggest that dark energy could be a remnant of the inflaton field, linking the early universe's inflationary phase with the current acceleration of cosmic expansion. Understanding the relationship between inflation and dark energy is a critical area of research in contemporary cosmology. As we ponder the mysteries of cosmic inflation and the shape of the universe, we are continually reminded of the importance of interdisciplinary collaboration and scientific inquiry. The exploration of these concepts involves contributions from cosmologists, physicists, astronomers, and philosophers alike. The synthesis of diverse perspectives enriches our understanding of the universe, highlighting the interconnectedness of knowledge and the shared pursuit of truth. As we reflect on our journey through the cosmos, we recognize the profound impact that cosmic inflation and the shape of the universe have on our understanding of existence. The interplay between science and philosophy invites us to contemplate our place in the universe and the mysteries that continue to elude our grasp. The quest for knowledge is a testament to the resilience of the human spirit, a reminder that our curiosity propels us to explore the unknown and seek answers to the most profound questions of existence. Looking to the future, the field of cosmology stands at the brink of new discoveries. Emerging technologies, such as next-generation telescopes and gravitational wave detectors, hold the promise of unveiling further insights into cosmic inflation and the nature of the universe. Projects like the James Webb Space Telescope are poised to revolutionize our understanding of cosmic structures, allowing us to peer deeper into the universe's history and the processes that shaped its evolution. The exploration of cosmic inflation and the shape of the universe encapsulates the essence of human inquiry. It is a journey that transcends disciplinary boundaries, inviting us to confront the mysteries of existence and our place in the cosmos. The intersection of science, philosophy, and the human experience enriches our understanding of the universe and challenges us to reflect on the profound questions that shape our reality. As we stand on the precipice of new discoveries, we are reminded that the universe is a tapestry woven from the threads of knowledge and curiosity. Each revelation not only expands our understanding but also deepens our appreciation for the intricacies of cosmic dynamics. The pursuit of knowledge is a journey without end, uniting us in our quest to uncover the mysteries of existence and the grandeur of the universe. The future holds the promise of further exploration and understanding, inviting us to continue our quest for knowledge and enlightenment. In the vast expanse of the cosmos, we find not only answers but also new questions that propel us forward in our exploration of the universe. The mysteries of cosmic inflation and the shape of the universe serve as a reminder of the beauty of inquiry, the interconnectedness of all things, and the enduring human spirit that seeks to unravel the enigmas of existence. We are left with a sense of awe and wonder. The cosmos beckons us to continue our quest for understanding, to seek out new horizons, and to embrace the beauty of the unknown. In this journey, we find not only answers but also new questions, inviting us to delve deeper into the cosmic enigma that defines our existence. The exploration of cosmic inflation and the shape of the universe is a testament to the human spirit's enduring quest for knowledge. It invites us to transcend the boundaries of our understanding, to contemplate the mysteries of existence, and to embrace the interconnectedness of all things. As we gaze into the cosmos, we find not only the answers we seek but also the profound questions that will continue to drive our exploration of the universe for generations to come. As we continue our exploration of cosmic inflation and the shape of the universe, it's essential to further examine the empirical evidence that supports these theories. The study of cosmic microwave background radiation, CMB, stands at the forefront of this endeavor, serving as a crucial window into the universe's early moments. The CMB is the remnant radiation from the Big Bang, a faint glow that fills the universe and carries with it information about the state of the cosmos when it was just a few 100,000 years old. This radiation provides an invaluable snapshot of the universe's infancy, offering insights into its temperature fluctuations, density variations, and the fundamental processes that led to its current structure. The first significant detection of the CMB was made by Arno Penzias and Robert Wilson in 1965, a discovery that fundamentally altered our understanding of the universe. The uniformity of the CMB across the sky suggested that the universe was once in a hot, dense state before undergoing rapid expansion, a direct confirmation of the Big Bang theory. Subsequent missions, particularly the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have mapped the CMB with unprecedented precision, revealing minute fluctuations that hint at the density variations seeded during the inflationary epoch. These fluctuations are critical for understanding the formation of large-scale structures in the universe. They represent the initial seeds of matter that eventually coalesce to form galaxies and clusters of galaxies. The analysis of the CMB's anisotropies has provided strong evidence for the inflationary model, as it aligns well with predictions regarding the statistical properties of these fluctuations. The patterns observed in the CMB also inform us about the geometry of the universe, helping to constrain the values of the density parameters that define its shape. Additionally, the power spectrum of the CMB reveals key features about the universe's composition, including the proportions of ordinary matter, dark matter, and dark energy. The baryon acoustic oscillations, BAOs, which are ripples in the density of visible matter, further enhance our understanding of cosmic structure formation. These oscillations arise from sound waves in the hot plasma of the early universe and serve as a cosmic ruler, allowing astronomers to measure the expansion rate of the universe and explore the effects of dark energy. The implications of this data extend into the realms of cosmology and theoretical physics. The combination of CMB observations and large-scale structure surveys enables scientists to test various inflationary models rigorously. They can examine the consistency of these models with observations and refine our understanding of the underlying physics that governs cosmic evolution. Notably, the data indicates that the universe is flat on large scales, further reinforcing the inflationary hypothesis, which predicts such a geometry resulting from rapid expansion. As we explore the shape of the universe, we also confront the concept of cosmic topology. The universe's topology refers to its overall shape and structure beyond simple geometric considerations. While the standard view posits a flat, infinite universe, alternative models suggest that the universe may have a more complex structure, such as a toroidal or multi-connected configuration. These topological possibilities raise intriguing questions about the nature of space and time, as well as the implications for cosmic inflation. For instance, if the universe is multi-connected, it may imply that traveling in one direction could eventually bring an observer back to their starting point, a phenomenon known as closed time-like curves. Such implications challenge our understanding of causality and the linear progression of time, echoing philosophical inquiries about the nature of reality. Investigating these topological configurations requires advanced mathematical techniques and sophisticated observational strategies, as current data from the CMB and galaxy surveys must be reconciled with potential non-trivial topologies. In contemplating the implications of cosmic inflation and the shape of the universe, we also encounter the concept of the anthropic principle. This philosophical consideration posits that the fundamental physical constants and properties of the universe appear finely tuned for the emergence of life. In a multiverse scenario, where countless universes exist with varying physical laws and constants, our universe's specific conditions may be a result of the anthropic principle. Essentially, we find ourselves in a universe that supports life because we are here to observe it. This idea leads to further philosophical reflections on the nature of existence and our place in the cosmos. The anthropic principle also intersects with discussions about cosmic inflation. If inflation leads to a multiverse, the variety of universes could help explain why our universe has the specific properties necessary for life. In this view, our universe may simply be one of the many that emerged from the inflationary process, with its own unique characteristics that enable the existence of life as we know it. This intersection of cosmology and philosophy opens the door to a deeper exploration of existence, reality, and our understanding of the cosmos. As we look toward the future of cosmological research, the pursuit of understanding cosmic inflation and the shape of the universe will undoubtedly continue to evolve. Emerging technologies, such as next-generation observatories and gravitational wave detectors, promise to unveil new aspects of the universe that were previously beyond our reach. These advancements will provide critical data to further refine our models of cosmic inflation and improve our understanding of the universe's fundamental structure. One of the most exciting prospects lies in the search for primordial gravitational waves, ripples in spacetime that could have been generated during the inflationary phase. Detecting these waves would provide compelling evidence for inflation, corroborating the theoretical framework and offering insights into the physics of the early universe. Projects like the Laser Interferometer Space Antenna, LISA, aim to detect such waves, paving the way for a new era of gravitational wave astronomy that could revolutionize our understanding of the cosmos. Furthermore, the exploration of dark energy, the mysterious force driving the accelerated expansion of the universe, will remain a critical focus in cosmology. Understanding the relationship between dark energy and inflation may hold the key to unraveling the ultimate fate of the universe. As researchers develop new observational techniques and refine their theoretical models, the interplay between dark energy, cosmic inflation, and the universe's shape will continue to be a captivating area of inquiry. In contemplating the vastness of the universe, we are continually reminded of the limitations of our current understanding and the potential for new discoveries. Each revelation not only expands our knowledge but also deepens our appreciation for the intricacies of cosmic dynamics. The journey through cosmic inflation and the shape of the universe invites us to embrace the unknown, to ponder the questions that arise from our exploration, and to seek connections between science, philosophy, and the human experience. We recognize the profound implications these concepts have for our understanding of existence. The interplay of science and philosophy encourages us to reflect on the mysteries of the cosmos and our place within it. The universe, with its intricate structures and enigmatic properties, remains a source of wonder, challenging us to confront the unknown and inspiring us to continue our quest for knowledge. Ultimately, the exploration of cosmic inflation and the shape of the universe exemplifies the beauty of inquiry. It invites us to transcend the boundaries of our understanding and to contemplate the interconnectedness of all things. As we gaze into the cosmos, we find not only answers but also new questions, propelling us forward in our exploration of the universe. The mysteries of cosmic inflation and the shape of the universe serve as a reminder of the enduring human spirit that seeks to unravel the enigmas of existence, fostering a sense of wonder and curiosity that defines our exploration of the cosmos. In this journey, we are reminded that our understanding of the universe is a tapestry woven from the threads of knowledge and curiosity. Each revelation enriches our understanding of cosmic dynamics and challenges us to reflect on the profound questions that shape our reality. As we move forward, the pursuit of knowledge will continue to unite us in our quest to uncover the mysteries of existence and the grandeur of the universe. The future holds the promise of further exploration and understanding, inviting us to continue our quest for knowledge and enlightenment. In the vast expanse of the cosmos, we find not only answers but also new questions that will continue to inspire generations of scientists, philosophers, and curious minds. The exploration of cosmic inflation and the shape of the universe stands as a testament to the human spirit's resilience and determination to seek the truth, no matter how elusive it may be. The intricate tapestry of cosmic inflation and the shape of the universe encapsulates the essence of our quest for understanding. It is a journey that transcends disciplinary boundaries, inviting us to confront the mysteries of existence and embrace the interconnectedness of all things. As we look to the stars, we find not only the answers we seek but also the profound questions that will continue to drive our exploration of the universe for generations to come. As we delve deeper into the mysteries surrounding cosmic inflation and the shape of the universe, it's important to consider the broader implications of these concepts for our understanding of time and causality. The inflationary model not only addresses the uniformity and isotropy of the observable universe but also raises intriguing questions about the nature of time itself. In the context of cosmic inflation, time is not merely a linear progression from past to future. Rather, it becomes intertwined with the fabric of space-time itself. The rapid expansion during inflation may have implications for the nature of temporal experience and the potential for alternate timelines or histories. One of the profound implications of cosmic inflation is the possibility that our universe may not be the only one. The idea of a multiverse, where multiple universes exist, each with its own physical laws and constants, has gained traction in modern cosmology. This concept suggests that the rapid inflation of our universe may have been just one event in a much larger cosmic tapestry, where different regions of space-time could undergo their own inflationary periods, leading to the birth of entirely separate universes. Each of these universes could have vastly different properties, potentially leading to entirely different forms of matter and energy. The multiverse hypothesis challenges our conventional understanding of reality. If multiple universes exist, it raises questions about our uniqueness within this vast cosmic landscape. Are there universes where the laws of physics are drastically different, leading to entirely different forms of life? Could there be universes that follow completely different evolutionary trajectories? This tantalizing idea pushes the boundaries of scientific inquiry and invites philosophical exploration about the nature of existence and the diversity of potential realities. Moreover, the multiverse concept is not merely a speculative idea. It has important implications for our understanding of fine-tuning in the universe. The fine-tuning problem refers to the observation that certain physical constants and parameters in our universe appear to be remarkably suited for the emergence of life. The existence of a multiverse could provide a natural explanation for this fine-tuning. In a vast ensemble of universes, it is statistically probable that some would have the necessary conditions to support life. This perspective shifts the focus from searching for a single, perfect explanation for our universe to considering the diversity and variety of existence across the multiverse. In addition to philosophical implications, the study of cosmic inflation and the shape of the universe opens the door to new scientific inquiries. For instance, researchers are now investigating how different inflationary models might predict observable phenomena. One such phenomenon is the potential detection of gravitational waves produced during the inflationary period. Gravitational waves carry information about the early universe and could provide a powerful tool for probing its origins. Detecting these waves would lend significant support to the inflationary model and deepen our understanding of the dynamics of spacetime. Furthermore, as we explore the fabric of spacetime, the role of dark energy becomes increasingly relevant. Dark energy, which is thought to be responsible for the accelerated expansion of the universe, is intricately linked to our understanding of cosmic inflation. Both phenomena involve the expansion of the universe, yet they operate on vastly different scales and mechanisms. Dark energy's effects dominate the current phase of cosmic evolution, while inflation occurred during the universe's infancy. Investigating the relationship between inflation and dark energy is an ongoing area of research that may yield profound insights into the universe's fate. As we contemplate the universe's shape, we must also address the role of observational astronomy in shaping our understanding. The universe is vast, and its exploration requires sophisticated tools and techniques. Ground-based observatories, space telescopes, and advanced simulations play crucial roles in unraveling the cosmic tapestry. Future missions, such as the James Webb Space Telescope, JWST, and the European Space Agency's Euclid mission, promise to revolutionize our understanding of cosmic structures and dark energy. These missions will enable astronomers to probe the universe's early moments, investigate the nature of galaxies, and map the distribution of dark matter and energy with unprecedented precision. The implications of these observational advancements extend beyond our understanding of cosmic inflation and the universe's shape. They also inform our grasp of fundamental physics and the underlying principles that govern the cosmos. The interplay between observational evidence and theoretical frameworks is essential for advancing our understanding of the universe and its mysteries. As we conclude this extensive examination of cosmic inflation and the shape of the universe, it is vital to recognize that the pursuit of knowledge is an ever-evolving journey. Each discovery leads to new questions, and the more we learn, the more we realize how much we still have to uncover. The interplay between theory and observation drives scientific progress, pushing the boundaries of our understanding of the cosmos. In summary, cosmic inflation and the shape of the universe stand at the forefront of modern cosmology, embodying the complexities and wonders of the universe we inhabit. From the rapid expansion that set the stage for the cosmos to the intricacies of its large-scale structure, these concepts challenge our perceptions and invite us to explore the very fabric of reality. As we continue our quest for knowledge, we are reminded that the universe is not only a realm of scientific inquiry but also a canvas for human imagination and curiosity. The mysteries of cosmic inflation and the shape of the universe resonate with a timeless truth: the pursuit of knowledge is an intrinsic part of the human experience. It is a journey that transcends generations, inviting us to engage with the cosmos, to ask questions, and to seek answers. The universe, in all its complexity and beauty, beckons us to explore the unknown and to uncover the secrets that lie beyond the stars. As we gaze into the night sky, we are reminded that each twinkle represents a story, a tale of cosmic evolution, of forces shaping the universe, and of the intricate dance of matter and energy. Our understanding of these phenomena is a testament to human curiosity and ingenuity, a reflection of our desire to comprehend the cosmos and our place within it. The exploration of cosmic inflation and the shape of the universe not only enriches our understanding of the cosmos but also encourages us to reflect on our own existence. It invites us to ponder the nature of reality, the interconnectedness of all things, and the profound questions that define the human experience. In our quest for knowledge, we are united by a shared sense of wonder and curiosity, propelled forward by the desire to explore the mysteries that surround us. As we stand on the threshold of new discoveries, the future of cosmological research is filled with promise. Each breakthrough, each revelation, adds another layer to our understanding of the universe. The mysteries of cosmic inflation and the shape of the universe will continue to captivate scientists, philosophers, and curious minds alike, inspiring generations to come. In essence, the journey through cosmic inflation and the shape of the universe serves as a reminder of the beauty of exploration and the endless potential for discovery. It embodies the spirit of inquiry that defines our humanity, encouraging us to venture into the unknown, to seek knowledge, and to embrace the wonder of the cosmos. The universe is a vast and intricate tapestry, woven from the threads of time, space, and the mysteries of existence. As we continue our exploration, we carry with us the legacy of inquiry and the unquenchable thirst for understanding that has propelled humanity forward throughout history. The mysteries that lie beyond the stars await our exploration, inviting us to uncover the secrets of the universe and to reflect on our place within the grand cosmic narrative. In this pursuit, we celebrate the journey of discovery, the joy of knowledge, and the profound connection we share with the universe around us. The exploration of cosmic inflation and the shape of the universe is not merely a scientific endeavor. It is a testament to the human spirit and its enduring quest for understanding in the face of the unknown. As we conclude this comprehensive exploration of cosmic inflation and the shape of the universe, we acknowledge the complexities and wonders that lie ahead. The universe is an ever-evolving landscape of mysteries, each waiting to be unveiled. The quest for knowledge and understanding is a timeless journey that transcends the boundaries of science and philosophy, weaving together the threads of curiosity, exploration, and human experience. In the end, the exploration of cosmic inflation and the shape of the universe invites us to contemplate the interconnectedness of all things, to embrace the wonders of the cosmos, and to continue our quest for knowledge with an open heart and an inquisitive mind. As we journey forward, we celebrate the mysteries of existence and the infinite possibilities that await us in the vast expanse of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.